Hey guys, this is Grant. Here's my problem. It's your first day on the job. You're replacing a guy who decided to drop out and go play baseball after he saw the ugly equation that you can get when trying a servo model to model this process that has a nested loop. We're at a chemical plant and we have a stream we need to heat up for a downstream process. In place, we have a big, expensive heater controlled with a PID controller. But we have a problem. The output stream is too far from the heater. So in the winter, since the pipes are outside, we're going to be losing too much heat by the time it gets heated up to when we're going to the output. But in the summer, it's fine. So we won't always need to use this adjustment that we're going to make to the process, but we'll be able to turn it on and off if we need to solve the problem. And we won't have to spend too much money on it. So we're going to be, let's just look at the system here now. Oops, there we go. So briefly, it's a PID right now, first process, which is a big heater. And then all over here is your output. We're going to measure here. And this is your measuring device. That is assumed to be perfect. So the problem is that we have a problem because it's losing heat and the temperature is too low right here. So we're going to be putting in a controller and a second process, which is a small, cheap heater. The controller we're going to be putting in is P only, all right? And we don't want to spend too much money. So officially, this is your inflow stream with a temperature, and then YM is going to be here measured, and then that's going to give off an error to your controller. See the difference between YD and YM. See if we need to turn on this controller, which is going to be a PID controller. Okay, and then that's going to give off a puff of air to the first process, which we're leaving as is, and that's a big, expensive heater. Okay, that's going to give off a that's going to give off an output that's going to go into the, this is where we're going to be adding our first element, and that is the second controller, and we're going to use P only because we don't want to spend a lot of money. Okay, that's going to give off a puff of air again, or a different puff of air going into the second process. Okay, and that's just going to be a small heater that we sometimes may not need it, like I said, but sometimes we do. Okay, this is your output temperature, and then here is we're keeping the measuring device the same, the one that we had. All right, and then we also need to measure if the second process was turned on or not, or after the output after the second process. We're going to call that H2 measuring device. That's going to feed back here, and then see if we need to adjust it or not, and then crank on the second heater or not. Okay, so we're saying that H1 is perfect, so we can assume 1. And then we also didn't spend much money on the second measuring device, so it's 10%, the temperature reading is 10% off. So we're going to be modeling it as 0.9 in our algebra. Okay, that looks pretty good. All right, so we have a nested loop here, which to fix that, or I mean, not to fix it, but just to simplify it down, we're doing our algebra. We're just going to treat all of that as, we're going to call that a separate loop and just call that loop A. And then let's see, that function, it's going to give you a function, we'll call that GA, is going to start here, go into the loop, and then the quickest way out of the loop is through GC, oops, I'll call this GC2, and then quickest way out of the loop is going to be through GC2, and then G2, and then it'll be out of the loop over here. So that function is just going to be GC2, G2, and then you're out of the loop, so then you're going to divide by your closed loop, which is going to be GC2, G2, H2, plus 1. Remember, this is 0.9, okay? So we have GA, And then let's get the function for the overall process. All right. And so that's function is going to be y equals yd because you're starting here and then it's times by this whole loop. And then that's going to, first thing it's going to go through GC1 and then G1. And then it's going to go through GA, which is everything in that blue loop. So we'll just keep that as GA. And then it's out of the loop right here. Divide that by your closed loop, GC1, G1, we'll use blue, GA, and then H1 now, and then plus 1. Remember, this is going to be modeled as 1. All right, so in this equation, this y equation here, what do we know? We know, we actually know GC1 and G1 because as we derived in class, G1, because it's a PID controlled process, G1, it's gonna be beta theta divided by theta s plus 1. All right, and then we also, like I said, we know GC1 because it's a PID. So from the derivation in class, we got GC1 is equal to KC 1 plus 1 over tau IS plus tau DS. Okay. All right. So then we're gonna plug in for, we're just gonna get rid of that right now and make that 1, and then so we have everything, we have something to plug in for everything because GA is right here. So then the next step is just going to be plugging this into this equation. And so that will give you YD times everything. And that is going to be, so GC1 is equal to KC 1 plus 1 over tau IS plus tau DS. And then times by G1, which is beta theta over theta S plus 1. All right, and then that is going to be multiplied on the numerator by GA. We're just going to leave that box to keep it a little more simplified. And then all of that denominator is right here. So that's GC1, G1, GA. And so that's actually going to be the same thing. So just write, okay, beta theta over theta s plus 1. Okay, and then times by GA again. And then you're gonna have your plus 1 again. And so now we're going to rewrite this GA equation over here. And then in the same sense that in this, we're going to use the same form as this equation and this equation to rewrite the GA equation from class. So to be doing this, we actually know G2 and GC2 from class. So that's going to be GC2 is equal to KC2. Why? Because it's a P-only controller. GC2 is. And then we also know G2 is equal to K2 over tau 2S plus 1. Okay. And then, and then H2 is just 0.9. And then we're going to just be, unfortunately, putting this, actually, we'll just rewrite this GA equation first. So GA is equal to K C2, K2 over tau 2S plus 1, and then over KC2, K2 over tau 2S plus 1, times by H2, which is 0.9. and then plus 1. Okay, so the now the next step that we're going to do is to put this into here. So get some more room. Okay, so y equals yd times everything. So that is going to be kc1 plus 1 over tau is plus tau ds beta theta over theta s plus 1. And then we have to times it by GA, which which will look like KC2, K2 over tau 2S plus 1, divided by KC2, K2 over tau 2S plus 1, times it by zero point 0.9, and then plus 1 for in the G of A term, or GA term, sorry. And then we have to do the denominator. Um, and then that is just going to be this KC1 plus 1 over tau is plus tau ds beta theta over theta s plus 1. Okay. All right. And then that takes care of everything here. And then we just have to times the GA. We're going to put our plus 1 so we don't forget that. And then the GA is just going to be the same thing as here. So I guess I'll just rewrite that quickly. Oh, shoot. I could just copy it, I guess. Okay. And then this is plus 1 is times everything. Oh, all right. Okay, so that's where I'm going to stop. The point being just, you can see how ugly these can get, but the point being that we know how to model this nested loop. Um, I was doing a servo response I should have talked about earlier. So if say there was a disturbance here, this would look exactly the same because for servo, D equals 0.